you guys hear me? So, over reading week, there are new restrictions for instructors. So I have to wear a mask too, even if I'm over here. So my only concern, of course, is can you guys hear me? If you guys can hear me, good, no problem. How about at the back? Can you hear me? Wonderful. Okay. So today is a nice, easy lecture. It's great. Before reading week, we had beams under axial load, nice and easy. And today we are doing linear elastic strain energy, nice and easy. The bad news is, after this, it doesn't get so nice and easy. What are you guys doing in 372 right now? Who's in 372? What are you guys doing? Anyone? Deflection? How do you solve for deflection? What method are you guys using? Moment area? Virtual work? Does that sound familiar?
Yeah.
Now what is virtual work based off of? Energy. So why do you think we're talking about energy today? Because our next unit is virtual work as well. But it's going to be different than what you learn in 372. In 372, you use virtual work to solve for deflection at a point. Right? Deflection at a point. In this class so far, we haven't cared about deflection at a point. We want deflection everywhere. And kind of before, I talked about the idea of those displacement functions. I said if we have displacement functions, we can then find the displacement gradient, then we can find the strain tensor, then we can find the stress tensor, kind of all the way through. And I said that later on we're going to have to figure out ways to find those displacement vectors. Well, we're going to use virtual work. So it's going to be a little bit different than 372. Again, 372 virtual work is a bit more simplified because you're looking for a point. For us, when we use virtual work, we are going to solve for the displacement everywhere. Everywhere. So it's going to be a lot of fun. That's kind of the last part of this course. How can we use these approximation methods to solve for displacements? But before we do that, we are going to have a little bit of fun. So we're going to switch over to here. And we're going to talk about the assignment that I didn't realize so many of you would struggle with. The assignment. If you guys looked at assignment 1, it looks like it was 2 questions to start. Question 1A, question 1B. But was there really much of a difference between those 2 questions? No. When it comes to these different beam scenarios, every beam we deal with, no matter what its fixity, can be solved using that differential equation. Every single beam. The only difference between these beams are, again, the boundary conditions. And those boundary conditions will affect those coefficients. So in the assignment, we had 2 different beams. We had simply supported, and we had fixed. Now, when it came to the differential equation for beams, how many constants do we have? 4. So that means we need 4 boundary conditions. Now, fun question for you guys. If you know what the moment was on a fixed beam, so this scenario, could you use that as a boundary condition? If you were certain the moment at one of those points. Remember, for the fixed beam, we didn't use a moment boundary condition. I'm just saying, if we did, let's say on an exam, I were to tell everybody that the moment at this point right here was 100 kilonewton meters, something like that. Could you use that as a boundary condition?
Yes.
Yes. Your boundary conditions, it doesn't matter where they come from, as long as they're true. So we're just going to go through these 2 examples really quick because these 2 are going to appear a lot more. So again, when we deal with beams, we need 4 boundary conditions. 4. The most obvious one is just a support in general. If I have a roller, what's the deflection at a roller? 0. How about a pin? Fixed end? A spring? No one likes springs, so don't worry, I won't give you a spring question. The first key concept is whenever you have a support, we know that the deflection is going to be 0. So y at 0 is 0. Y at L is 0. That's the first one. That's the most intuitive one. But again, we need 4. And this is where things start to change between the different types of beams that we have. Is this deflection boundary condition also valid for my fixed end beam? Yes. Is the deflection right here non-zero? No. So we know that this is valid for both when it comes to deflection. So y at 0 is equal to 0. Y at L is equal to 0. I'm very happy that I didn't have any questions about that. We'd have to go back a long ways if there's questions about that. The trouble becomes, what is the second boundary condition? What is the second boundary condition? When we deal with boundary conditions, they can be displacement, which we covered, but can they be rotation? Can I have a rotation boundary condition? Yeah. Why? Because rotation is related to deflection. Can I have a moment boundary condition? Yes. Why? No? Because it's related to displacement. It doesn't matter what my boundary conditions are, as long as I can relate them to displacement. Can I have a shear boundary condition? Well, let's take a step back. Is shear related to displacement? Yes. It's the third derivative. So could I have a shear boundary condition? Yes. So it's just a matter of analyzing what you have and then applying the correct boundary conditions. When it comes to the deflection of a simply supported beam, we know it's going to look something like this. So here's a fun one. If my load is uniform, so there's nothing crazy going on, what is my rotation at the midpoint? Let's put it this way. I'm going to go in green. Right here at the midpoint, my beam is perfectly flat. What is my rotation right at the midpoint? 0. So could you use that? Yes. You can use a lot of different things as long as they are typically correct. But we typically don't use that because what we usually do is we do the actual boundaries. So if we look at these two boundaries, I have 2 pins. Is my rotation at these 2 pins 0? No. As we can see, there is that slope downwards and then that slope upwards. But if we were to draw the moment diagram, what would it look like for a simply supported beam? Don't make me get the Eng 130 lecture videos out. I'll do it. Maybe the second pin's throwing you off. Simply supported. Who has a 374 midterm today? When is it, sorry? Last night? Oh, I thought today was Monday. I'm like, it was on Sunday? No, it's Tuesday. It's Tuesday, okay. So if you guys had the midterm for structural design and you don't know this moment diagram, I'm really sorry. You may have bigger problems than this assignment. No one? No one knows a moment diagram of a simply supported beam. Looks like the opposite of the deflection, yeah. It's basically just a parabola. Just like that. So what is the moment at both my ends? 0. A hinge cannot restrict rotation. So it's just 0. So right here, I had students say, okay, well, y double prime is equal to 0. Is that true? I see some yes, I see some no's. Is that the definition of moment, y double prime? Ooh, now everyone's getting decisive again. Does that look better? Yes. When you go from deflection to rotation, it's just a derivative. But once you go lower, you have to add EI. And it makes sense, right? If I want to go from moment, well, actually, let's put it this way. In Eng 130, did you deal with elastic modulus or moment of inertia? Did you deal with deflections in Eng 130? No. But were you able to get the moment diagram in Eng 130? Yes. So it's not just as simple as taking derivatives. At some point, if we want to go from moment to deflection, we actually have to start considering the stiffness. So that would be that one. If we were to come down to this beam down here, this will be a lot of fun because I know, well, actually in 374, have you dealt with frames? Frames? Perfect. What's the moment for a fixed beam? You were happy 2 seconds ago. Yeah, I've seen frames. Now you don't know the moment diagram. This is essentially a frame right here. If I were to bring this down, it's okay. I'm giving you a hard time because I can. I'll erase it. It's going to look something like this. Now, is the moment at both ends 0 in this case? No. If I told you the moment at both ends, could you use it as a boundary condition? Yes. So you can't use moment because it's not relatively given, but if we look at the deflection, it kind of goes something like this. Now, is the rotation at both ends 0? So yes. So we know that y prime at 0 is equal to 0, and same at the other end. This is why at the beginning, when we started this, I said you, although you didn't believe me, will prefer fixed, even though it's indeterminate, because the boundary conditions are simpler. I couldn't believe, well, I felt bad for you guys in the assignment because a lot of students expected question 1 and question 2 to be completely different, but they were the exact same. The only thing you had to change in your code was these green boundary conditions. Just 2 changes in your code, you'd be good to go. A lot of students didn't quite figure that out, so I'm sorry. Which leads me to kind of my topic that I want to discuss. I'm concerned for you guys. I'm concerned for you guys. How are you guys doing? Y'all look defeated. Any more midterms? Wednesday. Who would do that? Well, sorry, what midterm do you have on Wednesday? Soil mechanics. It'll be fine. Soil mechanics is essentially this. I prepared you for soil mechanics. Well, not at all. But here's my point, is I've seen the grades, and there has been a decrease over the first and second midterm. There's also been a decrease in assignments. Is it me? Have I not done a good job with, I guess, the second half of the course so far? It's one of those things that I can see that you guys are getting tired. You guys are getting burnt out, and I'm sorry for that. So what I'm going to do is I'm going to propose some changes to our lecture schedule. Not only to help you guys kind of take a load off, but to also help you guys with assignments. The number one problem I got in assignments, besides how to define X1, you have no idea how many emails I got for that, it's just Mathematica. And that's fair enough. I have my assignment guide videos, but I didn't really teach you Mathematica. So that's on me. So I apologize to you guys. These assignments can be difficult if you don't know Mathematica. And even though I have my assignment guides that show you Mathematica, perhaps it's not enough. So here's kind of the scenario that we have. After today's lecture, we have basically 3 more theory lectures that will be tested. We have virtual work for continuums, virtual work for beams, and the Rayleigh-Ritz method. And then after that, I was planning to go right into finite element analysis. Finite element analysis is very complex and will not be tested. I've told you guys this before. So here's what I propose. We push finite element to the back end of the course, and we do more examples of Rayleigh-Ritz and virtual work. More examples. How does that sound to you guys? Would you guys prefer more examples of something that's going to be tested and then push the theory of something that won't be tested later? All right, I'm seeing a lot of yes. So this is what I want to change. So the two in green here are going to be 2 lectures where we're just going to do Rayleigh-Ritz and virtual work in Mathematica. That's it. We're going to look at some scenarios, and my hope is that if we do them together, your assignments will be a piece of cake. That's all I want. The Mathematica errors that I got through email were very simple. Again, it was just very clear that you did not just not understand the concept, you just didn't understand Mathematica. That was it. So I want to do 2 examples together using virtual work. Now what would happen is this would push our 2 finite element lectures to December 7th and 8th. Are you fine with that? Most people are saying yes, but there is one drawback, and that is this. Assignment 11, the bonus assignment, is finite elements. So basically, all you will have for that assignment is my assignment guide video. We won't be going through Abacus in time in lecture. Is that a sacrifice you're willing to take? All right, I'm seeing more yes. Okay, so we will stick with this schedule. If you want, of course, if you have any questions about finite elements, if you're doing the bonus assignment, you can ask me at any time. Happy to help. The assignment is basically using software. Just using software. The software will be available for download on the eClass page today. It's a pretty beefy download, so if you want it, or if you want to start soon, I'd download it soon. If you're on Mac, I'm so sorry, I have no idea how to make it work on Mac. But you guys are what, 3rd and 4th years? You already know that Mac is not very good for civil engineering. How is AutoCAD? Yeah, not so much fun. All right, so this is going to be the new schedule. Again, we will do 2 lectures just using Mathematica. I'm thinking to really help you guys, because again, I see you are struggling, the questions that we do in those 2 lectures will be your assignment question. How does that sound? If we can go through the assignment question together and have it done by the end of the lecture and you don't have to worry about the assignment for the rest of the week, will you be happy? Perfect. That's all I want. I want you guys to be happy. You guys started off happy, and it's just like the weather. It just went down, down, down. Now look at you guys. It's terrible today. I'm honestly surprised you're even here. Oh, I'm really sorry that you had to come in this early. Okay, so I will update the lecture stuff on eClass to reflect this. And then I'm also thinking towards the final exam. And what I want to do is I want to record each lecture topic. I know when I look at the videos online, they can be hard to see the actual content, especially since I made it in PowerPoint and then trying to do it on an iPad. It doesn't really convert over too nicely, so sometimes let's be honest, it looks like garbage. So what I want to do is I want to record each lecture video individually so that you guys have that to study for rather than going through the live recorded lectures. But one of the things that I would want to ask your opinion on, because the Eng 130 kids seem to like it, in my videos, do you want me to have my webcam on? Like, do you want me to actually be there, or do you just want like the voiceover? Who thinks webcam? I don't care either way. It's the same video. I just have to click a button. Okay, who wants just voiceover? All right, I see 2 just voiceover, no webcam, no webcam. It stings a little bit, guys. No, I'm just kidding. I'm just kidding. I find for these kind of topics, I prefer it that way. In the Eng 130 videos, I put the webcam in the corner, and I blocked like 2 words. And I had this guy comment on every video. The instructor needs to learn not to cover the words. It's like, it's 2 words. You can figure it out intuitively. But oh well. You get used to dealing with internet trolls, so. All right, so we're going to go into today's lecture. Again, it's nice and simple. It's linear elastic strain energy. And I talked about this at the very beginning, that the reason why we're doing this isn't because this is its own topic. It's more because this will prepare us for the last half of the course. Again, we have two major things. Virtual work, which you guys have taken in 372, and you've already said is based on energy. The second one is the Rayleigh-Ritz method. Who wants to take a guess at what that's based on? Anyone? Energy. A lot of these approximation methods are going to be based on energy. So we need to become familiar. If you come out of this lecture, what we're going to see is we are basically going to derive equations for the energy or stored energy inside of something. If I were to take this, actually, what can I do? Here. Does my hat right now have energy? Yes. Remember from high school, what kind of energy would it have right now? Potential or kinetic? Potential. Because if I were to release it, it drops, right? mg times h. Well, it's the same thing for a linear elastic material. If I were to take something, I don't really know what, maybe this, and I were to fold it, does it have stored energy right now? Yes, because if I were to release it, it goes back to its original position. This came in handy. So basically that's what we're going to talk about today. When I load an object, I'm storing energy inside of it. And if it is linear elastic, once I release the load, it'll go back to its original position. Now, the amount of stored energy is actually what's going to be used in a lot of calculations. For virtual work, you say that the internal virtual work is equal to the external virtual work. Ring a bell? Yes. Today, that internal virtual work, that is actually linear elastic strain energy. So we're basically determining what that is. So strain energy in linear elastic materials. We've already talked about it, but I haven't given you the formal definition. The general equation, so the key here is general, for calculating strain energy in a uniaxially stressed material is the integral from 0 to epsilon 1,1 of sigma 1,1 with respect to epsilon 1,1. Now the key here is this is the general formula. Does this apply to inelastic? What do you guys think? Does this apply to inelastic? Yes, this applies to everything. In your assignment this week, I give you basically a nonlinear material, concrete. And I ask for the strain energy in concrete. Now, is concrete elastic and linear? No. So for that particular equation, or that question, all you have to do is this. Because if you look at the question, I give you what the stress formula is in terms of epsilon, and all you have to do is integrate from 0 to whatever strain you want. So in the question, in the assignment, I say I want the peak strain, and then I want the crushing strain. So all you would do is just change the limits of the integral. But who likes doing integrals? Put up your hand. Who's a big fan? Like Clayton, yeah, I'm very excited to do this. No one. That's why when we have linear elastic materials, things become nice. Because if I have a stress strain curve, what is this formula basically implying that the strain energy is equal to? If I'm taking a function and integrating it, what am I finding? Area under the curve. So all this is the area under a stress strain curve. So for concrete, it's parabolic, but it's the same concept. I'm just finding the area under that parabola. Well, it's nice for us in this course, linear elastic materials. So if I were to do a stress strain curve of a linear elastic material, sigma 1,1 and epsilon 1,1, what's it going to look like? What's this bad boy going to look like? Linear and elastic. If it's linear, can it be curved? No. It's just going to be a linear line. Linear, elastic. So if this is the case, and by this definition, my strain energy is the area underneath the curve, well, what shape do I have? Triangle. Do you guys know the area of a triangle? Yes. It's just like the moment diagram of a simply supported beam. You should know it. So if this is the case, and for linear elastic materials, this is just the area of a triangle, well, our integral equation is actually just 1/2 sigma 1,1 times epsilon 1,1. Do I need to integrate anything? No. That's why I said today is a nice, easy lecture, for the most part. Because when it comes to strain energy in linear elastic materials, this is going to be the equation we use if it's a uniaxial case. Now I got a couple questions. This is nice and easy because linear elastic. Would I give you something that's nonlinear? What do you think? Is nonlinear fair game? Yes. Do I give you something nonlinear in your assignment? Yes, concrete. Can I give you something nonlinear in your exam? I could, but I won't. I could, but I won't. So when it comes to the assignment, you'll use this. But for the exam type scenarios, I'm only going to be testing linear elastic, okay? So don't worry about it too much. So we're saying, okay, this is great. But then we have the second kind of problem, uniaxial stress material. So if I was just pulling something in one direction, this would be my expression. So how do I go from a uniaxial stress state to a triaxial stress state? What do you guys think? Let's put it like this. We just covered epsilon 1,1. So let's say I hold it like this, vertically. I get my response, get my equation. Let's say I take the material and I put it horizontal, so 2,2, and I were to pull it. Is everything going to be the exact same? Just replace 1,1 with 2,2? Yes. So the nice thing for us is to go from a uniaxial stress state to a triaxial stress state is all we have to do is sum up all the terms of all the components. So basically this will be our equation in general format where it's the same as above. So this first part here is the same over here, but instead of just having 1,1, we sum it over all the terms. So question for you guys, in this format, how many terms will there be? How many integrals? Who thinks 3? Okay, who thinks 6? Who thinks 9? Who thinks 12? Who doesn't care? Some people. There will be 9. And the reason why is because we don't just have one index, we have 2. So basically we have this is 1 and this will be 1, 2, 3. So we have 3. This will be 2 and then 1, 2, 3. There's 6. This will be 3, another 1, 2, 3, 9. And that makes sense because how many components do we have in our Cauchy stress tensor? 9. How many components do we have in our strain tensor? 9. So it makes sense. It's basically just all the components. Now again, this right here is the general formula. If we have a linear elastic material, we can simplify it to the following. So if I were to ask you guys on an exam or anything else, tell me the stored strain energy of a linear elastic material, this is all you will use. Now let's look at this formula. Do you guys know what 1/2 is? Does that scare you? 1/2? No, it doesn't scare you guys. What about the stress components? If I were to give you the Cauchy stress tensor, do you have all the stress components? Yeah. What about the strain tensor, which we talked about? If I give you the strain tensor, do you have all the components? So is there really anything in here that's too bad, too scary? No. You are now experts on finding the Cauchy stress tensor and the small strain tensor. And if you have those two, all you have to do is multiply each component together. It's pretty simple, actually. So if we were to look at a continuum, and we were to look at this formula, even though you won't tell me right now, I know some of you guys are thinking, Clayton, that looks disgusting. Who likes it when formulas have a summation in them? No one, because no one knows what they mean. I had to go through and show you guys. But what's nice is we can actually just expand it. So again, all this is just going through the indices. So it's sigma 1,1, epsilon 1,1, plus sigma 2,2, epsilon 2,2, so forth. all the components. So this right here, it is long, but is it that bad? No, because this even right here can be simplified. It has 9 components right now. 9. Think to our Cauchy stress tensor. Our stress tensor has 9 components. But how many different components are there? 6. Why? Symmetric. So right here, if I have sigma 1, 1, or sorry, sigma 1, 2 times epsilon 1, 2, and then I have sigma 2, 1 times epsilon 2, 1, are these two components the exact same? Yes. We know that sigma and epsilon are symmetric, so we get this formula right here after we combine all the symmetric terms. We just have to add 2. Again, it's nice and simple. And this kind of goes back to, I actually didn't get asked this, but I thought I would. Clayton, in our strain vector, when we are going from stress to strain, we have a 2. So this is why. Symmetry, right there. So we can take a look at this, and this is what's going to be typically on exams. Do I have a relationship between sigma 2, 2 and epsilon? Yes. Do I have a relationship between my small strain epsilon 1, 2 and my engineering strain gamma 1, 2? Yes. We'll start with that one. Engineering strain is simply 2 times epsilon ij, so we can replace the 2 times epsilon 1, 2 with just gamma 1, 2. And you guys already said that, hey, we also have an expression that relates stress to strain. So if I wanted to, I could write my strain energy in terms of only stress components. But here's where the fun begins. If I know the stress components, do I know the von Mises stress? So could I ask you guys to express this in terms of von Mises stress? Could I ask you guys to express this just in terms of strain? Yes. Could I ask you guys to express this in terms of a bulk modulus? Yes. This is where strain energy becomes fun. There is many, many ways to express it. So that's what you'll typically see on exams. Now, if we were to look at this, I already gave you guys how it is expressed in terms of stresses. Sigma, 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 sigma. On an exam, I can say, okay, what is this in terms of epsilon? So that's kind of the fun thing about strain energy. Now, the last thing we're going to talk about for strain energy in a continuum is this. Oh, actually, no. Two things. Deviatoric and volumetric strain. I always forget about this one. Let's see if we can have a little reminder. Let's see how much you guys remember. Actually, I was going to put a wager on it, but I really think you guys will know this. Let's see. Deviatoric stress. What does that do to my body? Change the shape or change the volume? Shape. Volumetric stress or strain. Change the volume, change the shape. Volume. So you guys already know. See, good thing I didn't put a wager on it. So basically, the stored strain energy, which we just discussed, can actually be split into 2 components. Deviatoric strain energy and volumetric strain energy. So if we were to take a look at what our stress tensor was, we said it was actually deviatoric stress tensor plus a hydrostatic stress times I, where P, not I, P, is just the average of the normal stresses, which is simple. So basically, our stress tensor can be expressed as the following. Now, if I were to take this relationship between my sigmas and I were to plug it into our strain energy equation, we get the following. And then what I can do is I can rearrange it into the following format. So every time I had a P, 1, 2, 3, I just factored it out and threw it at the end. Now, what happens is this first component right here is the deviatoric strain energy, and the second one is the volumetric strain energy. I had to go through this because this was on your assignment. It's not used too much, but again, it's something to be aware of. Now, you guys are doing the assignments, and question 1 asks for these 2 parameters. Who wants to calculate this? No? No one wants to calculate this? No one has all that extra free time in their lives? No. But what's nice is this actually simplifies in quite nicely. The deviatoric strain is simply the von Mises stress squared divided by 6G. Does that make sense? That something deviatoric would be related to von Mises? What do you guys think? Does that make sense to you guys? When we had a state of hydrostatic stress, so just P, 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 everything else was 0, what was my von Mises stress? 0. So does it make sense that the deviatoric stress is deviatoric related to von Mises? Yes. If we look at volumetric, it's going to simplify into simply P squared divided by 2K. And again, this makes sense because our bulk modulus K was related to the volumetric strain. So simplifies quite nicely. In your assignments, I believe you were given G as well as K. So all you have to do is find P and von Mises. And a quick question for you guys. If you have the strain tensor, can you find von Mises and P? Yes. So that's kind of the first question. Nice and simple. Now to the fun part. And this is where I'll start to lose some students. So buckle up. Total strain energy. Total strain energy. When we just did those calculations, did they take into account the geometry of our body? Was there something in there that had moment of inertia, the height, anything like this? No. If I were to take this podium and I were to stress it, it's going to have some strain energy. The roof above you also has some strain energy. Which one has more? The roof. It's much bigger. Much bigger. So the total strain energy in a body is basically the strain energy which we just derived times its volume. Okay, that's the concept. That strain energy we just defined, think of it like a density. That is the strain energy per unit volume. So if I want the total strain energy, and I have basically its density, all I have to do is multiply it by its volume. But it gets a little bit tricky. Remember when I give you a beam under axial load? Beam under axial load. Did I just always give you a nice rectangular beam? Or did I give you something that changes as a function of x? Gave you something that changes. I know, put you to sleep. So basically, again, the stored strain energy, which we just derived, is the stored energy per unit volume. If we want the total strain energy, we need to integrate over the domain of our shape. So if I want my total strain energy, it's going to be the integral over the domain of that strain energy we just derived. Now this right here looks confusing. Integral omega dv. How do I calculate that? Is this deceiving? Let's put it this way. If I have a three-dimensional shape, three dimensionals, can I calculate its volume using only one integral? Think back to math, what is it, 209, 201, calculus 3, when they gave you stuff like integral of a cone, or the volume of a cone. How many integrals did you need? No? Wow, that must be repressed pretty deeply. 3. One for every dimension. One for every dimension. So if we had an Euler-Bernoulli beam, and I were to use this formula, we said in our slides that we define our axis as follows, where it goes from 0 to L in x1 direction. It goes from negative h over 2 to h over 2 in the x2 direction. And in the into the page direction, it had a thickness b. So is this clear so far? How we defined Euler-Bernoulli beams? Yes, hopefully. If I wanted a total strain energy and I knew what U bar was, so this same formula, well, this would actually be this. Again, all I'm doing is integrating over every direction. So these are in backwards order. I realize this now. So it'd be the integral from 0 to b in the x3 direction, not x1, x3. Then the integral from negative h over 2 to h over 2 in x2, and then the integral from 0 to L in the x3 direction. Is that a lot of fun? No? Wait till you guys see virtual work next lecture. Looks like some hieroglyphics. Doesn't even make sense to me. Things are about to get fun. I hope that Yong Lee's been treating you nicely, because I'm about to become him. All right. So this looks terrible. But what we're going to do is we're going to discuss certain cases, like Euler-Bernoulli beams, because it actually simplifies quite a bit. For an Euler-Bernoulli beam, have you ever seen the cross-section vary as a function of x? Euler-Bernoulli beams, beams under flexure. Have I ever given you a varying cross-section? No. Beams under axial load I have, but not Euler-Bernoulli beams. So if that's the case, and the area isn't a function of x1, x2, or x3, can I just take it out? Yes. So that's what we're going to do, is we're going to look at some of those scenarios. So let's look at beams under axial load first. We said that, okay, if I want the total strain energy, all I need to do is integrate the strain energy over the domain. And we have a nice expression for that strain energy. So we're going to figure out what exactly it is. From our lecture, which is just before reading week, we said that the strain tensor is going to be as follows, and the stress tensor is going to be as follows. Now remember, when I found strain energy in linear elastic materials, it was just each component multiplied by each other. If this is the case, isn't the strain energy going to become really nice? What do you think? Is strain energy going to look really bad or really nice? Nice. Because again, it's every component multiplied by each other. What's 0 multiplied by 0? How about 0 multiplied by 0? 0. And it just goes on and on. There's only actually two components we need to consider. So again, we go to our formula, and after we do that, we realize that there's only two components, epsilon 1, 1, sigma 1, 1. So it's going to be as follows, E times epsilon 1, 1, which is 1/2 of E times epsilon 1, 1 squared. It's a uniaxial case. Now what's nice is we know what epsilon 1, 1 is. It's the derivative of u with respect to x1. So we know that our strain energy is going to be as follows. Nice and simple. So if we want the total strain energy, again, we go back to our formula. We're just integrating what our stored strain energy is over the domain. And if we were to look at this first part right here, 1/2 of E. Does E, our elastic modulus for linear elastic materials, change over the volume? Let's say that this was a steel beam. Is this point going to be different than this point when it comes to my modulus? No. It's going to be constant throughout the beam. So if it's constant throughout the beam, just like 1/2, can I just take it out? Yes, I can just take it out because, again, they are not a function of the volume. The second part is the integral over the domain. But again, we said for beams, we already know what this is. So we're going to take out the 1/2 of E, and then we're going to put in our actual domain. Now, where it gets a little bit more fun is this. We only have one component we're integrating, just one. If we were to look at this one component, which is our displacement, is it going to be a function of all three of these? No. When we derived this concept of beams under axial load, we took a horizontal case. We took our beam and we pulled it horizontally. So is this going to be a function of x2? If I'm pulling it along x1, is it going to be a function of x2? No. Is it going to be a function of x3 into the page? No. It's just going to be a function of x1. I know that looks really, really bad. So if this is the case, and this is just a function of x1, I can actually pull it out of these two right here and have it over here where I'm integrating with respect to x1. And this becomes nice because if I'm just integrating nothing with respect to x3 and with respect to x2, that integral right here, oh, this can come out nicely. This is just our cross-sectional area. I'm just integrating from 0 to b, so that thickness, which will just give me b. And then I'm integrating from negative h over 2 to h over 2, which will just give me h. So it's just going to be base times height, which is area. So at the end of the day, for beams under axial load, this is our total strain energy. Now this is in its nicest form, or not, no, it's meanest form. Because typically, if area is constant, can I take area out of here as well? Yes. So if area is constant, I can take this out of here. It's nice and simple. Now again, we will use this a lot in our coming lectures because this is how we're going to solve for the displacement U1 later on. What about Euler-Bernoulli beams? Well, it's actually going to be basically an identical process. We know what epsilon is. We know what sigma is. Therefore, we can find our strain energy. Now, our strain energy is, again, the summation of all the components. So we're going to have this component multiplied by this component. But where it gets nice is even though we have this component, it's multiplied by 0. So even for Euler-Bernoulli beams, it's just going to be those two components. It's going to be 1/2 sigma 1,1 times epsilon 1,1 because these are the only two non-zero components. We know that for a uniaxial case, we can have epsilon times, E times epsilon 1,1. So the exact same thing as before. The difference is the definition of epsilon 1,1. We know that's equal to 1/2 of E times this squared, or we can simplify it into 1/2 of E x2 squared and then multiplied by the derivative squared. It's a mouthful to say. It's not fun. So then we are going to integrate it over our domain to get our total strain energy, and it's going to be almost identical. Can I take these out? 1/2 times E. Are you sure? Positive? Yeah. I gotta make sure you're not sleeping. So yes. And then the domain, well, we already talked about the domain, so we have this right here. Now again, for Euler-Bernoulli beams, was it a function of x3? No. Was it a function of x2, our deflection? Actually, this is a great question to ask you guys. For beams under axial load, I kind of just left it, but you just did the assignment for Euler-Bernoulli beams, and you had your deflection function. Was it a function of x1 and x2, or just x1? Who thinks both? Who thinks just one? It was just x1. The shear, the shear and the moments were a function of x2, but the deflection itself was just a function of x1. So if I were to differentiate it with respect to these two, well, it would essentially do nothing. So I can take this out of these two and kind of pop it to the end here, and then we're left with this right here. Now this will be a fun one for you guys. Oh, I wasn't supposed to have this. I was going to ask you what this is. But if you were to go look at any sort of textbook, this is the definition of moment of inertia. So if I were to substitute that in, I get this equation, which is almost identical to before. Now this is the proper equation, but how many times have you seen moment of inertia vary throughout the cross-section? Not once. I've never given it to you. So this can actually be factored out if constant, which it typically is. So that's the total strain energy for an Euler-Bernoulli beam. Again, where does this come into play? Well, the Rayleigh-Ritz method is almost identical to virtual work. It has some differences. But basically, in virtual work, we take internal virtual work and we make it to external virtual work. The internal virtual work is basically this. The only difference is instead of y, which is our deflection function, we would have y star, which is our virtual deflection function. So there's going to be a little bit of change to this when it comes to virtual work. Now, when it comes to the Rayleigh-Ritz method, which is the one we do at the very end, it's based completely on total strain energy. So in that lecture, we'll use this formula basically directly. So that's why we do it. Now, that is it for kind of the theory. We'll go into the example, and there's basically just one. Where is it? Here. Nice and simple, because again, this is a simple topic. There isn't too much to do. Again, the whole goal of this topic is to get you ready for the next topics. So we're going to go through this. It says a linear elastic isotropic material is under the following state of stress. If G, E, and nu are the shear modulus, Young's modulus, Poisson's ratio respectively, determine the volumetric strain per unit volume and the deviatoric strain per unit volume. Where do we begin? I like this because this right here is a great exam question. Remember, exam questions aren't supposed to be those big, long questions. They're supposed to be able to be solved in 2 to 3 minutes. Where do we begin? We have a stress tensor with only one non-zero component, sigma 2, 3. So where do we begin? Volumetric strain. Does anyone remember the formula for volumetric strain? Oops. I don't expect you guys to know it. It's P squared divided by, what is it, 2G? I get this one and the other one mixed up sometimes. P squared divided by 2G. We already said in the question that you can just leave G as it is. So what's the only unknown that we have in here? It's kind of deceiving. Let me change this right here, because this isn't really that. Let's just call this sigma 2, 3. So what's our only unknown in this equation? The G is fine, 2 is 2. Yes, question? Is it 2K? Oh, yeah, you're right. Thank you. Our only unknown is P, the hydrostatic stress. What is the hydrostatic stress from the stress tensor? 0. Remember that hydrostatic stress is equal to sigma 1, 1 plus sigma 2, 2 plus sigma 3, 3 divided by 3. It's the average of the normal stresses. And if I were to look at my normal stresses, well, they're all 0. So we know that this is going to be equal to 0. So what is my volumetric strain? 0. I put 0 at the top, 0 divided by 2K. It's going to be equal to 0. Ooh, that's a bad 0. See, how was that? Lots of fun. Strain energy is a lot of fun. Let's go about the second one. Come down here. The deviatoric. If we look at the formula, which I have over here, this is the one divided by G. And it is sigma von Mises squared, all divided by, what is it, 6G or 2G? I don't remember. 6G. Again, G is fine. We just need that von Mises stress. If I have a stress tensor, can I figure out what my von Mises stress is? Who thinks no? No one? You guys are looking at me like I'm an idiot. Fairly aggressive today. What happened? Let's talk about it. You guys need to talk about it. This is the last question. It takes us 2 seconds, and I got 25 minutes. I will fill it as long as I can, because I got nothing to do. How was the exam yesterday? Come on, someone has to talk about it. I'm here. Do I need to get the tissue box? Or wonderful? What was on it? Beams? Composite sections? Those are fun. Nothing like doing concrete, even though you've never learned concrete. No? Oh, that's too funny. At least for me, I know you guys are really hating it. But we're almost done. Like, isn't that nice? What did you do over reading week? Have fun? You say that, I don't believe you. What did you do? That was so much fun. Yeah, it's not fun. Anyone do anything fun over reading week? Cookies. See, that's fun. You guys need to do more fun things. Get all of reading week. Opportunity missed. You know what I did over reading week? Oh, you have no idea. Where is it? I'm going to show a picture. Oh. See, that's fun. Studying's not fun. I can't lose my progress, though. I don't remember where I was. Just maybe too far. My point is, get a hobby that's not studying. What are you going to do when you go to work and then you come home at 5 and have nothing to do? Study what? You guys have to learn how to have fun. You're young adults. You're not old like me. You're going to look back and say, wow, I wish I listened to Clayton and had some fun. Because it doesn't matter. You're going to have your degree. I have my degree. Does it say what I got in 374? No. You guys are looking at me like I was about to say yes. No. Your degree just says you have a degree. Have fun. That's the key thing right now. How many of you guys have worked before? Perfect. You all have jobs. So what's the big deal? No? You guys are saying Clayton, he's an idiot. No? Have fun. Trust me. Time will go by fast. How many of you guys have 2 years left to graduate? All right, couple. How many have 1 year left? How many of you have 3 years left? Okay, so the point is you have years left to graduate. It'll be gone in a blink of an eye. Trust me. And then you're going to say, wow, that happened fast. Then you're going to blink again, you're done grad school. Blink again, you're teaching 398. It happens way too fast, and it gets kind of scary how fast time goes by. So make sure you're enjoying yourselves. I don't trust that you're enjoying yourselves. The emails I get from you guys are I can feel the sadness. Like through an email, you know how hard that is to do? So please, 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 do something. How could I entice you to find something fun? Okay, well, you want to challenge me? Yeah. If I get over half the class sending me an email of something fun that they did, I will give you all 100% on the bonus assignment. The gauntlet has been thrown. And if you say studying, I'm going to give everyone a 0. Because that is not fun. You guys have to do something fun. I played Call of Duty with the first years. You know how toxic that is? All in the name of making sure that they have a good time. Did I have a question? Is there a question? No? Yeah. Gotta wait till the recording's finished. Come on. I'm sick of getting in trouble by the university. All right. But yes, anything that's not studying, something that's outside of school. But we'll go back to the question. The von Mises stress. You guys are smart. I try and ask you guys for the answer, but no one wants to talk to me. You guys are too cool for me, just like the first years. So if we were to look at this, if I have every component of my strain tensor, can I find von Mises? Yes. So if I were to go down, sigma von Mises is going to be equal to, the first component is sigma 11 minus sigma 22 squared, 0. The second one is sigma 22 minus sigma 33, 0. Like, isn't this just nice? Going through. Next one's going to be 0, which is sigma 11 minus 33. And then we have plus, 6? Times all the shear stresses squared. What is sigma 12? What is sigma 23? Sigma 23. So it's going to be 0 squared plus 0 squared plus sigma 23 squared. Nope. It's so hard to write. I don't know why I write sideways. Perfect, divided by 2. So a lot of this is going to cancel. What is 6 divided by 2? 3. Nice. And this is times sigma 2, 3 squared. And we still have a square root. So now all we have to do is just substitute this into our equation above. So we get that u is going to be equal to square root of 3 sigma 2, 3 squared divided by 6g. You say, okay, what is the square root and then squared? Does it just cancel? Yeah, just cancels. So this is going to be equal to 3 sigma 2, 3 squared divided by 6g. What is 3 divided by 6? 3 divided by 6. 1/2, yeah. Come on, guys. You guys scare me sometimes, I'm not going to lie. Divided by, oops, scare myself writing this stuff, 6g. Perfect. So again, strain energy is not bad because the only real question I can ask, whoa, that is really big. Scary. The only real question I can ask you in an exam is just to give me the strain energy. And if I give you sigma, then you're good to go because you can find epsilon. If I give you epsilon, you can find sigma. What happens if I ask you for the strain energy and I don't give you either? Yeah, not enough information. So I have to give you one of the two. And if I give you one of the two, you can find strain, or you can go back and find stresses. This is basically just plug and chug. That's why when I talked about kind of the revised schedule we're going to do for this class, I didn't do a Mathematica portion for strain energy because there isn't really any coding. You can do the whole assignment this week by hand. Sure, you may not like an integral, but that's all it is. Yes?
Are you going to have a final review?
Final review. I thought about that. That was actually going to be the wager, but you guys answered that correctly. Do you guys want a final review? So all 8 of you can show up? No, it was nice. No, it's fun. I will give you a final review if that's what you guys want. I have to go try and track down some of the finals. If you look on or eClass, I think I hid it because I'm still trying to find them. I didn't really have access to the old ones. I only had 2. So I'm going to go try and track down more for you guys. But I can definitely do a final review. Which leads me to my next thing I want to talk about, and I forgot, so this helps. Do you guys still want a multiple choice? Yeah? I thought about this, because I knew that you guys would want a multiple choice. Would you want it multiple choice but written? Meaning that, well, I've never seen it in university, but you know in high school where you answer multiple choice, but you have to justify your answer with some work kind of thing? So I wonder if you guys would want that, so that I can give partial marks. For instance, let's say that I asked you this exact question right here. I had answer A, B, and C. And let's say that if you were to write beside the question the formula, well, then I can give you half the marks because I knew what you were trying to do, even though let's say you get it wrong. Yes? All I would be looking for is kind of the final answer. So let me try and think of, let's go down here and let's say that I wanted the stress tensor and I give you displacement functions. So all I give you, or I'll give you position functions. All I would want is for you to show like u is equal to x minus x, and then just give me the final answer. And then from there, u is equal to kind of the partial. Basically just give me final answers so I can follow what you did. I wouldn't be asking for the exact work. It's basically I just want some excuse to give you guys marks. I can't just go to the university and say, yeah, I gave them all 50% on the question because I trust that they were doing it right, even though they got the answer wrong. So what do you think? Yes?
Would it be like submitting a written paper as well, or like answer box on the class?
So that would be the thing, is it would have to be kind of written, and you have to scan and upload. But to do that, I would give you guys an extra 10 minutes or so. Well, from what I've seen, a lot of people use their tablets and stuff, so they can just convert to PDF. It's up to you guys completely. Again, I just want an excuse to give you partial marks. If you were to write just a formula down or just some of the steps in between, it shows to me that you know what you're doing, and maybe it was just a calculation error. For instance, you guys remember the midterm question that was something like 3x1 plus 4x2 plus 6x1 is equal to, I don't know, what was it, C? How many of you guys would have gotten that right if you just trusted me? Probably quite a bit. Everyone thought I made a mistake. I wrote that question like, oh, this will be fun. But it's one of those things that if you were to, let's say, actually said, you know what, Clayton made a mistake, this is x3, and if you were to just show your work, I could have still given you 3.5 out of 4. Like, it's one of those things. Because I guarantee that if you think I made a mistake, you still have the right process. So is it really fair that you get a 0? Well, not really. At least in my opinion. So all you'd have to do is just show me your work. Yes?
What if you didn't show work and you just guessed, but you got it right? Would you still...
Yeah, no, you still get full marks. Like, the showing your work is just to try and get bonus marks. Not bonus marks, but just try and get extra marks.
Yes.
Yeah, perfect. So we all agreed? You guys would be okay? So I'll distribute the exam as a PDF file. You guys do it, and then submit it. And then I'll mark it by hand. It's not fun for me. I got to mark all your exams just before Christmas, just before I fly out to Phoenix. Oof. Anyone do travel yet? No? I haven't flown in like, 2 years? So I'm curious how that process is now. You guys are too busy, apparently. Yes?
Do you know, like, whether or not the finals are going to be mostly online? Like, is it just dependent on the class?
Yeah, it's dependent on the class. We got a request from the university basically saying, what do you want to do? I said it'll be online because we have online students. I don't know how I can do something in person and online while keeping it fair. Because and I actually talked to the first years, and I'm curious about your opinion, is let's say that I made you come in right in person. I give you guys 3 hours, you do the exam, and 3 hours, you hand it in. But for the online students, they would have to submit it. So you have to give them that submission time. But let's say I give them 10 minutes to submit. For some people, submitting takes 30 seconds. So then they get 9.5 minutes of extra time that you don't have. So that's where it becomes a real mess. Well, I say, well, everybody gets 3 hours. Well, then the online students complain because they need time to submit. I don't know how they're going to do that. Engine 130 is a mess right now because a lot of people cheated on their second midterm. They have 2 midterms now. Well, I was with you guys. We only had 1 midterm. But there was a lot of cheating. So now they're trying to do in person, but as you guys know, the restrictions just got worse because I have to wear a mask now. But they're trying to do 1,200 kids in a room together. So that's something I have no idea what they're going to do. That's why I figure online for all is just the way to keep it most fair. That's what I want to do, just keep it fair. I know it's not ideal, but it's fair. So yeah. Any other questions about the final? This is good. It's on E-Class. It's December 16th. December 16th from 2 to 5, 3 hours. It's going to be 50 questions, with 30 of them being on these last topics. I think I said 5 questions is going to be from topic 1 and 2, so the first midterm. 15 questions from topics 3 to 6, and then 30 questions from 7 to 10. Might have a bonus question in there. Any questions at all? No? Perfect. So everyone's good with a hard copy exam. You do it by hand, and then you submit it. It's all going to be multiple choice, so you just circle whatever answer is, whatever you think is correct. All right, perfect, because that way I can give you partial marks, which is what I want to do. I know that a lot of you guys may have had just one simple mistake and you get 0 out of 4. It's tough. So let's try and avoid that. All right, perfect. All right, well, that's it for this lecture. It's a little bit early. Again, today's easy, but come Thursday, it gets a little gross, so be ready. All right, you guys have a wonderful day.